Hello, this is team number 10, and we are gonna present our project, Cooking the Perfect Steak. We are inspired by the scene in 흑백 요리사 from Netflix, where Chef 안성재 says 고기가 이분하게 익지 않았어요. We thought we could optimize the cooking process of grilling meat on charcoal. To do so, we focused on two parameters, grilling time and resting time. Also, this involves calculating and simulating the heat transfer process. First, grilling involves conduction within the meat, radiation from the heat source, and convection on the meat surface. These mechanisms heat the steak and trigger a Maillard reaction. During resting, the primary heat transfer mechanisms are conduction from the surface to inside and convection from surface to atmosphere. This step is critical for achieving an even internal temperature. To summarize, cooking involves multiple heat transfer mechanisms: radiation, conduction, and convection. Our goal is to control these processes to create a perfectly cooked steak. We used three equations for conduction, convection, and radiation. To solve the equation, we set initial and boundary conditions. Initial temperature of meat to be 5 degrees Celsius, 800 Kelvin for temperature of heat source, and 300 Kelvin for ambient temperature for resting. For properties of meat and Maillard reaction, we calculated thermal diffusivity and specific heat based on the composition of meat, water, protein, and fat. The Maillard reaction occurs at temperature above 130 degrees Celsius. Core temperature of 55 degrees Celsius is required for medium rare doneness. The optimization parameters are grilling and resting times. Initially, we fixed the number of grilling cycles as allowing the algorithm to choose cycles resulted in extremely short grilling times. All times were set in a matrix format, enabling us to optimize without breaking each process into separate steps. Flipping was set at half the grilling time. We excluded Maillard reaction since the surface already reaches high temperatures during grilling due to the heat source.
Our analysis starts with defining the bounds for grilling and resting times. Each step calculates temperature changes using the finite difference method FDM based on heat flux from radiation and convection. For evaluation, we calculated the temperature distribution, standard deviation, overcooked penalties, and the deviation from the target core temperature. MATLAB's built-in genetic algorithm GA function was used to optimize these parameters, ensuring a robust solution. The main function initializes constants and parameters. It then sets the objective function and runs the optimization process to minimize the error in achieving the target temperature distribution. Next, the objective function is defined. It evaluates the temperature simulation results, penalizing overcooked regions and deviations from the target temperature. This ensures that the algorithm prioritizes uniform doneness while avoiding overcooking. The evaluation function calculates penalties for regions with temperatures above 55 degrees Celsius and the inner 90% of the steak. These penalties are added to the errors calculated from deviations in standard deviation and target core temperature. Overcooking penalties were weighted heavily to minimize overcooking. The total error was computed as the sum of penalties and temperature distribution errors. The optimization function minimizes this error, ensuring the steak is cooked evenly without overcooking. Heavy weights were added to penalties to prioritize uniform internal cooking. In the simulation, grilling times are divided into two phases. Each side is cooked for half the grilling time, then the temperature is updated. During resting phases, temperatures are also updated iteratively, ensuring realistic modeling of heat transfer inside and outside of the steak. Temperature updates during all phases are conducted using one-dimensional FDM, dividing the steak into 40 grid points across its 4 cm thickness. Radiation and convection heat transfers are applied to each side of the steak during grilling, while we assume that convection is applied to both surfaces during resting. On the right is the result of the temperature distribution inside the steak over time. Now, on the left side, we can see the optimal grilling time of each grilling steps and optimal resting time for each resting steps in matrix. The optimized grilling and resting times produce the steak with a uniform internal temperature close to the desired 55 degrees Celsius. The results were validated through simulations, confirming the effectiveness of our approach. In conclusion, our optimization process successfully achieved the optimal grilling and resting time for the uniform doneness inside the steak while avoiding overcooking. Future works could include refining the mathematical model, for example, using three-dimensional FDM analysis for better modeling, and extending this method to other cooking techniques such as pan grilling. Thank you for your attention, and we welcome any questions.